Hello everyone, welcome to our Mechanism Sessional group project. This is Assignment 5 of our 5th semester course ME29002. The topic we have chosen is Railway Ladder System, and this project is being presented by myself, Sayyid Faiz Raza Zaidi, and my teammates Swayam Nagar and Krishna Choji Patla. First, let's start off with discussing the project roadmap. We shall begin with evaluating the problem statement and the technical approach to the question. Then we'll synthesize this on Linkage software followed by simulation on Fusion 360. We'll then build a physical prototype of the same and suggest some further modifications and areas of innovation. That's all, handing it over to Swayam.
Now let's move on to the problem statement. Our main objective is to address the difficulty of passengers while boarding or deboarding the trains when the platform height does not match the coach floor level. For this, we need a simple mechanical ladder system that can assist the passengers safely into the coach. Additional goals we could develop is to automate the deployment and retraction of the driver link using a motor or actuator. And another goal could be including a locking mechanism so that the ladder could hold the load of the passengers once it is deployed, reducing the strain on the motor. Our technical approach is divided into three major stages: concept design, synthesis, simulation, and final prototype development. We began with the concept design, where we selected a hinged foldable ladder mechanism capable of fitting beneath the coach body. The idea was to use a set of linkage that would allow the steps to swing outward and downward smoothly when activated by a small motor. Next comes the most crucial stage, which is the synthesis and simulation. Here we use the linkage software to verify the motion paths, linkage lengths, and step orientations. This step helped us to ensure that the mechanism deploys correctly without collision or tilt. After validating the kinematics, we moved to Fusion 360, where we created 3D models of all components and ran a motion analysis to confirm clearances and feasibility. Finally, at the prototype stage, we built a small-scale physical model using mount board and pin joints. This model allowed us to visualize the ladder's working motion and verify that the linkage system behaves as expected in real life. In this part, I will briefly explain our synthesis process in the linkage software, where we verified the motion paths, linkage lengths, and the step orientations. The main challenge in designing the ladder mechanism was ensuring that the steps remain horizontal throughout the motion, regardless of how the ladder unfolds. To achieve this, we synthesized a system of parallel links and 4-bar mechanisms. Here, FD is the driver link, and the 4-bar mechanism consists of FD, CB, CD, and the ground link FB. We began by defining two extreme positions of the top step. This one is a fully deployed position, and once I run this, it retracts into the fully retracted position. These two configurations were used to determine the pivot points and the link lengths using the two-position synthesis. Once the upper step's motion was finalized, we replicated the same link logic for the lower step. This creates a synchronized movement where both the steps deploy in a controlled and a coordinated manner without tilting or interfering with each other. This software allowed us to animate this mechanism in real time, such that we could check for smooth rotation of all the joints, ensure the step orientation remained constant, and confirm that the overall motion stayed within the geometric constraints. We also made sure that the 4-bar linkage follows the Grashof criterion. With the synthesis complete and validated, the design was ready for 3D modeling and prototype realization.
We start by importing the final DXF sketch from the Linkage software into Fusion 360. Using this sketch as a reference, we extruded each link to create a consistent model of the mechanism. Standard dimensions were applied during modeling. For example, the ladder width was kept at around half a meter, with each step surface modeled to have a usable width of about 250 millimeters. In the mechanism layout, we use a single central driver crank, which acts as the input link. All the remaining links were arranged symmetrically on both sides of each step. This ensures balanced motion, reduces twisting, and keeps deployment stable. Once the model is assembled, we checked for smooth rotation at all pivot joints using the joint constraints and motion study in Fusion. We introduced a rotation limit for the input driver crank, restricting its motion to 30 degrees, which is sufficient to fully deploy the ladder without causing interference, and also helps in control actuation when operating manually or with a small motor. Finally, we verified that the overall movement remained within the geometric constraints of the underside of a train coach and the typical lower bound height difference from an Indian railway platform.
For the physical prototype, we used mount board to represent the links and pins to act as pivot joints. This helped us quickly verify the actual motion of the mechanism outside the software environment. The prototype clearly shows both the folded and deployed positions. And by rotating the central driver link manually, we were able to confirm smooth movement of all the connected links. Although simplified, the model helped us validate the basic working principle and visualize how the ladder would behave when mounted under a train coach. So these are some practical modifications we have considered to enhance the functionality and the reliability of the ladder system. First, the ladder can be automated using a small motor or actuator which is linked to the coach door sensor, so deployment and retraction happens only when required. Next, we can add a load-off locking system which uses a simple mechanical latch to hold the ladder firmly once it's fully deployed. It also removes the load from the motor and increases its service life. For safety, we can integrate basic sensors. A piezoelectric strip can detect any obstruction during deployment and stop the motion immediately. And an IMU sensor ensures that the ladder operates only after the train has fully come to a halt. We can also include a manual override lever so that the ladder can still be operated if the motor or any linkage fails. Finally, adding small dampers at the driver link helps absorb sudden jerks during loading and unloading, protecting the motor and improving long-term durability.
We also wanted to try out mechanism synthesis in a coding environment, which is why, as a small bonus, we also tried implementing a Viper mechanism simulation entirely through Python. The script models a standard 4-bar Viper linkage by defining the link lengths, pivot positions, and the rotation speed of the input crank. For each frame of the animation, the code uses basic trigonometry to compute the positions of all the joints as the input link rotates. The visualization shows the moving links, highlights each joint, and even shades the region swept by the Viper braid so that we can see the actual coverage on the windshield. Using Matplotlib's animation tools, we were able to generate a smooth, continuous motion that directly reflects the underlying kinematics. This exercise helped us understand the mechanism mechanically and also demonstrate that linkage synthesis can be prototyped just as quickly as CAD by using simple Python code.
On that note, we conclude our presentation. Hope you liked it. Thank you.